Every second, invisible bullets pass through your body, charged particles from dying stars 60 light-years away. Radiation from explosions that happened before Earth existed. Space is armed, and it has been firing at us for 4 billion years. A magnetic shield wrapping our planet is the only reason life continues, and right now it is weakening. From rogue black holes drifting through the galaxy to a single cosmic burst capable of stripping our atmosphere in minutes, this changes how you see the sky. If you enjoy this, like and subscribe. Prepare yourselves, we begin. Space looks empty. It is anything but. Between every planet, every moon, every rock in our solar system, something moves. Always. The vacuum of space is threaded with radiation, charged particles, magnetic fields, and streams of plasma travelling at hundreds of miles per second. You cannot see it. You cannot feel it from the surface. But it is there, constant and relentless, pressing against everything in its path. Start with the basic picture. When astronomers say outer space, most people imagine nothing. Pure black, total silence. But every cubic inch of space near our sun contains anywhere from 5 to 10 particles per cubic inch. That sounds tiny. It is not. Multiply that across the 400 million miles between Earth and Jupiter, and you're looking at an ocean of invisible matter in constant motion. These particles are mostly protons and electrons fired off by the sun. They stream outward in all directions at speeds averaging around 250 miles per second. That stream has a name, solar wind, and it does not stop at any border. It fills the entire solar system, from the sun all the way to a boundary called the heliopause, roughly 11 billion miles out, where solar influence finally loses its grip. But solar wind is just the most familiar ingredient. Space also carries magnetic field lines stretching and twisting across millions of miles. It carries X-rays and ultraviolet radiation. It carries high-energy cosmic rays, fired from violent events happening in distant galaxies. Particles so energetic they should not exist by the physics we use in laboratories. One of those particles, detected over New Mexico in 1991, carried the same kinetic energy as a baseball thrown at 50 miles per hour. One single subatomic particle. Scientists named it the Oh My God particle, and nobody has fully explained where it came from. Now zoom out. Our solar system does not sit in a quiet corner of the galaxy. It moves. Right now, the Sun is carrying Earth and every other planet through the Milky Way at around 500,000 miles per hour. As we move, we plough through regions of different density, different radiation levels, different magnetic environments. Space around us changes constantly. We are not stationary targets. We are moving through a live fire range. What keeps all of this from killing everything on Earth immediately? A magnetic field. Earth generates one from its churning liquid iron core, and it wraps the planet in a protective bubble called the magnetosphere. Solar wind hits that bubble and bends around it. Cosmic rays get deflected. Charged particles spiral along field lines and dump their energy near the poles, which is why we see the northern lights. The aurora is not decoration. It is the visible evidence of an invisible war happening overhead every single day. Without that field, Earth would look like Mars. Mars lost its magnetic field billions of years ago. Solar wind stripped its atmosphere layer by layer over millions of years. The oceans evaporated. The surface became a frozen, irradiated desert. The same process would happen here. Every breath you take exists because Earth's core is hot enough to keep spinning liquid metal and sustain a magnetic field. That field is not guaranteed forever. Scientists have been watching it weaken for centuries. The measurements are clear, the trend is consistent, and the implications are significant. Because here on Earth, that protective bubble has done something strange before. It has shut down almost entirely. And when it did, the consequences reached every corner of the planet. You're inside a storm right now. It started 4.5 billion years ago when the sun ignited, and it has never stopped. Every second, the sun sheds roughly 1 million tons of material in the form of charged particles. Those particles blast outward at speeds between 200 and 500 miles per second under normal conditions. During an eruption, that speed jumps to over 2,000 miles per second. Earth sits inside this permanent outflow. The storm is the environment. There is no version of our solar system without it. Solar wind is not wind in any way you experience on Earth. It carries no air, no moisture. It is plasma, a fourth state of matter where electrons have been ripped away from their atoms, leaving a charged, highly energized stream of protons and electrons moving in near lockstep with the sun's magnetic field. When that stream reaches Earth, it arrives at roughly 93 million miles from the source. The journey takes 2 to 3 days. During large eruptions, it can arrive in less than 18 hours. Earth's magnetosphere deflects most of it. The day side of the magnetosphere gets compressed by the incoming pressure, pushed to roughly 40,000 miles above the surface. The night side stretches out into a long magnetic tail, extending millions of miles behind Earth in the opposite direction of the Sun. The shape is roughly like a comet, blunt on one side and swept back on the other. Inside that bubble, Earth exists in a slightly different environment than the open solar wind outside. But the magnetosphere is not a solid wall. Solar wind particles squeeze through at the poles, where field lines converge and dip toward the surface. These funneled particles collide with atmospheric gases at altitudes between 60 and 200 miles up, energizing those gas molecules and making them glow. Oxygen glows green and red. Nitrogen glows blue and purple. The result is the aurora borealis in the north and the aurora australis in the south. The aurora is beautiful. It is also a reminder that the barrier is imperfect. During periods of heightened solar activity, solar wind intensifies. The sun goes through roughly 11-year cycles of activity, swinging between solar minimum, when eruptions are rare, and solar maximum, when the sun becomes unpredictable. During solar maximum, the frequency and power of solar eruptions increases significantly. Satellites in low orbit experience increased atmospheric drag because the upper atmosphere expands under solar heating, creating more resistance. GPS signals become unreliable. Radio communication at certain frequencies drops out entirely. These are not hypothetical risks. They happen routinely and are currently managed by space weather forecasting services that track solar activity around the clock. In 2003, a series of powerful solar eruptions hit Earth in rapid succession. Power transformers failed in South Africa. Airlines rerouted flights away from polar routes. The International Space Station crew retreated to shielded sections. Satellites experienced malfunctions. This was a significant event. It was nowhere near the most powerful eruption the Sun has ever aimed at Earth. The Sun operates on long cycles beyond the familiar 11-year rhythm. Some researchers track 200-year cycles and longer periods of elevated output. The current solar cycle has shown stronger than predicted activity in its early stages, and the peak is still ahead. But raw particle output from the Sun is just one piece of what space is throwing at Earth. There is a separate class of solar event, far more violent and far less predictable, that has already demonstrated exactly what it can do to a civilization that depends on electricity. Picture a bubble wrapped around an entire planet. You cannot see it, touch it, or feel it, but every living thing on Earth owes its existence to this structure. Earth's magnetic field extends tens of thousands of miles into space in every direction. On the side facing the Sun, it pushes back against the solar wind at a boundary called the bow shock. On the night side, it stretches into a vast magnetic tail. Together, this system forms the magnetosphere, and it is the only thing standing between life on Earth and the relentless particle radiation pouring out of our Sun. The field is generated deep inside the planet. At Earth's core, temperatures reach around 10,000 degrees Fahrenheit, as hot as the surface of the Sun. That extreme heat keeps the outer core liquid, and that liquid is mostly iron and nickel. As Earth rotates, this molten metal moves. Moving electrically conductive material through a magnetic field generates more magnetic field, which drives more movement, which reinforces the field further. Scientists call this process the geodynamo. It has kept Earth's magnetic shield running for billions of years. The strength of the field is not uniform across the planet. It is strongest near the poles and weakest near the equator. There is also a large and well-documented weak spot called the South Atlantic Anomaly, centered over South America and the South Atlantic Ocean. Over this region, the inner radiation belt dips unusually close to Earth's surface, and satellites passing through it experience higher rates of radiation damage and electronic glitches. The International Space Station crew receives elevated radiation doses as the station passes through this zone. Space agencies actively monitor it. The South Atlantic anomaly has been growing and drifting for decades. Some researchers believe it may be an early indicator of what happens before a geomagnetic reversal, an event where Earth's magnetic north and south poles physically switch positions. This is confirmed by the geological record. Earth's magnetic field has reversed hundreds of times over its history. Scientists know this because when volcanic rock cools and hardens, magnetic minerals inside it align with the existing field and freeze in place, recording the direction of north at that moment. Reading ancient lava flows like a tape recorder, geologists have mapped dozens of reversals over the past few 100 million years. The last full reversal happened roughly 780,000 years ago. During a reversal, the field does not simply flip overnight, it weakens first. Over thousands of years, the field strength drops significantly, potentially to as little as 10% of its current strength. During that window, the protective bubble shrinks. More cosmic radiation reaches the lower atmosphere. More charged particles from the sun penetrate to the surface. Life survived previous reversals, but previous reversals happened before global telecommunications, electrical power grids, and $6 trillion worth of satellite infrastructure orbiting the planet. The current field is measurably weaker than it was 2 centuries ago. Since scientists began formally measuring it in the early 1800s, the overall field strength has dropped by roughly 9%. The rate of weakening has accelerated over the past few decades. Some models suggest that if this rate continues, the field could drop to reversal transition levels within the next couple thousand years. Others argue that timeline could be shorter. Whether a reversal is approaching or not, the field has proven it can weaken. It has proven it can fail partially. And when external forces hit a weakened magnetosphere, the results are not subtle. Something already happened once that showed exactly how catastrophic that combination can be. The compass needle pointing north has not always pointed north. At some point in Earth's history it pointed south, then north again, then south. The magnetic poles have wandered, stalled, and flipped dozens of times, and they will do it again. This is one of the most disorienting facts in all of Earth science. The planet's protective magnetic identity is impermanent. It is a temporary configuration, and right now the evidence suggests it is shifting. The geological record holds this history in stunning detail. Across ocean floors and lava fields on every continent, magnetic minerals locked into ancient rock tell the story. Each layer of cooled volcanic material carries a magnetic fingerprint from the moment it solidified. Line those layers up in sequence, and you get a timeline of the magnetic field going back hundreds of millions of years. What that record shows is that reversals are irregular. They can happen as frequently as every 10,000 years during certain periods, or remain stable for 50 million years during others. There is no reliable schedule. What the record also shows is that reversals are not instantaneous. They involve a prolonged period of instability during which the field weakens substantially, breaks up into multiple poles scattered across the surface, and oscillates before stabilizing in the new orientation. This transition period can last anywhere from 1,000 to 15,000 years. During that time, the magnetic protection Earth normally provides is severely degraded. Modelling what happens to Earth's surface environment during that transition paints a challenging picture. With the field at a fraction of its normal strength, the magnetosphere shrinks. The bow shock that normally sits 40,000 miles above the surface compresses toward the planet. Solar wind particles that normally get deflected begin reaching the upper atmosphere in much larger quantities. Cosmic ray flux at the surface increases. The ozone layer, which is partially maintained by the electromagnetic interactions that the magnetosphere regulates, becomes vulnerable to accelerated degradation. Evidence from ice cores in Antarctica and Greenland shows that previous reversals correlate with periods of increased cosmic ray exposure. Some researchers have proposed that these episodes were linked to elevated mutation rates in certain species and increased rates of climate fluctuation. The connections are actively debated in the scientific community, and the data is not yet definitive enough to state a direct causal chain. But the correlations exist and have drawn serious attention. What is not debated is the practical consequence of a significantly weakened field for modern technology. Current infrastructure was built assuming a stable, strong magnetic field. Electrical power grids operate on physical transformers, many of which are large, specialized, and take months to replace. A sustained reduction in field strength paired with elevated solar activity would expose those transformers to radiation-induced currents at levels far above design tolerances. The same applies to satellite constellations, aviation, communication networks, and anything microchip-dependent operating at high altitude. The South Atlantic anomaly already demonstrates the elevated failure rate electronics experience in regions of reduced magnetic shielding. Scale that anomaly to a global phenomenon, and the engineering challenge becomes enormous. Right now, the North Magnetic Pole is moving. For most of the 20th century, it drifted at around 10 miles per year. In recent decades, it has accelerated to roughly 35 miles per year and has been tracking towards Siberia. Geophysicists updated the World Magnetic Model ahead of schedule in 2019 because the pole was moving faster than the model predicted. That movement alone does not confirm a reversal is imminent, but something is clearly changing inside the planet, and outside it, something even less predictable is already hitting us constantly, from every direction, at nearly the speed of light. Right now, something is passing through you. Cosmic rays arrive at Earth from every direction, at all times, without pause. They are not rays in the way light is a ray. They are particles, mostly protons, but also heavier atomic nuclei stripped of their electrons and accelerated to extraordinary velocities. Some travel at 99.9% of the speed of light. They arrive from supernovae, from the jets of active galaxies, from colliding neutron stars, from sources not yet identified. Some of the highest energy particles observed cannot be explained by any known source within a plausible distance from Earth. These particles are small, but speed is energy, and some cosmic ray particles carry so much energy that when they slam into the upper atmosphere roughly 60 miles above the surface, they trigger a cascade. One high-energy particle hits a nitrogen or oxygen nucleus and shatters it, releasing a shower of secondary particles. That shower fans out across miles of atmosphere, multiplying as it descends, until thousands or even millions of secondary particles arrive at ground level from a single original hit. Scientists call this an extensive air shower, and detectors on the ground can map these cascades across areas the size of cities. At sea level, cosmic rays are significantly filtered by the miles of atmosphere above. The average person at sea level receives a small but real dose of radiation from cosmic rays annually. At higher altitudes, the filtering thins. A person living in Denver, roughly 1 mile above sea level, receives about twice the cosmic ray dose of someone living at the coast. Flight crews on transatlantic routes receive the equivalent of several chest X-rays worth of cosmic ray radiation per year from accumulated flight hours. The particles that make it through are capable of doing real damage. High-energy particles passing through biological tissue can ionize molecules along their path, breaking chemical bonds and causing damage to DNA. Most of this damage is repaired by cellular mechanisms. Some is not. The background cosmic ray dose is believed to be one contributing factor to the baseline rate of certain cancers in the human population, though isolating it from other radiation sources is difficult. At the altitudes where astronauts operate, the doses are dramatically higher. Astronauts on the International Space Station receive radiation doses roughly 200 times higher than people on the surface. During long-duration spaceflights, such as a mission to Mars, the cumulative dose from galactic cosmic rays alone would exceed current, acceptable career dose limits under current safety standards. This is one of the most significant unresolved engineering challenges in deep space exploration. Cosmic rays also interact with electronics. High-energy particles passing through a computer chip can flip a binary digit, changing a 1 to a 0 or a 0 to a 1. This phenomenon, called a single event upset, is rare at ground level but measurable. In spacecraft and high-altitude systems, these errors happen more frequently and have caused real failures. Engineers use error-correcting memory and radiation-hardened chips to compensate, but the problem never fully disappears. For most of Earth's history, the magnetic field has provided a partial buffer, bending the paths of lower-energy cosmic rays before they reach the atmosphere. During periods of weakened magnetic shielding, more of these particles penetrate deeper into the atmosphere, increasing surface exposure. That relationship between field strength and cosmic ray flux is not theoretical. It is measured directly. The Sun also influences cosmic ray flux. During high solar activity, the solar magnetic field expands and provides additional shielding for the inner solar system. During solar minimum, that shielding weakens, and galactic cosmic ray intensity at Earth measurably increases. The connection between solar activity, magnetic shielding, and particle radiation is continuous and dynamic, but the Sun itself can generate something far more targeted than background cosmic ray flux. When the Sun erupts, it does not just increase the general particle environment, it fires a directed, concentrated burst of radiation at whatever happens to be in the way. 35,000 feet above the Atlantic Ocean, the sky is a different place. Airline passengers at cruising altitude sit beneath roughly 2.5 times less atmosphere than people at sea level. That atmosphere is not decoration. It is a radiation shield built from hundreds of miles of air molecules, and every 1,000 feet of altitude removed means less protection from the particle radiation streaming in from space. At cruising altitude, the cosmic ray dose rate is roughly 50 to 100 times higher than at sea level. For the occasional traveller, this dose is negligible. For a pilot who flies 300 hours a month for a 20-year career, it accumulates into something that regulatory agencies take seriously. In the United States, the Federal Aviation Administration classifies flight crew as radiation workers, the same category as X-ray technicians and nuclear power plant operators. Studies comparing cancer rates in airline crews have produced mixed results over the years, but several large studies have found elevated rates of specific cancers, particularly melanoma and breast cancer in female crew, in populations with long-term flight careers. The research is ongoing. The mechanism by which cosmic rays cause biological damage is relatively well understood. A high-energy charged particle passing through a cell leaves a trail of ionized molecules. DNA strands struck directly can suffer the double-strand breaks, the most serious form of DNA damage. Cells have repair machinery for this, and the vast majority of such breaks are correctly fixed, but repair is not perfect. Occasionally, the repair introduces an error, a mutation that the cell retains. Most mutations are harmless or eliminated by the immune system. A small number are not. At ground level, cosmic rays are a minor contributor to the overall radiation environment compared to naturally occurring radioactive materials in soil, rock, and building materials. At high altitude, the proportion shifts. For passengers on a polar route from the United States to Europe, flying over the Arctic where Earth's magnetic field funnels cosmic rays more directly toward the surface, the in-flight dose can reach the equivalent of a dental X-ray for a single long-haul flight. During heightened solar activity, the situation changes rapidly. When the Sun fires a large solar particle event, the radiation environment at altitude can spike to dozens of times its normal level within minutes. Airlines monitor space weather forecasts and can reroute or descend aircraft to lower altitudes during severe events. Several notable flights have done exactly this in recent decades, but the radiation picture is more complex than just the body. Cosmic rays interact with electronics in ways that have direct consequences for safety-critical systems. A single energetic particle flipping a bit in a flight control computer is a low-probability event, but at scale, across hundreds of thousands of flights per year globally, the cumulative risk is not zero. Aviation systems are designed with redundancy partly to account for this. The risk is managed, but it exists. Beyond aviation, the electronics used in satellites, weather monitoring systems, and communication relays are permanently exposed to the full cosmic ray environment with no atmospheric filtering at all. Satellite operators regularly deal with anomalous resets, unexpected bit flips, and component degradation caused by particle radiation. Some satellites have been lost entirely to radiation-induced failures. As human activity moves further from Earth's surface, this problem only grows. Any permanent base on the Moon would sit outside the magnetosphere during certain phases of the lunar orbit, fully exposed to the cosmic ray environment and to sudden solar particle events. Designing habitats, suits, and electronics that can operate indefinitely under that exposure is one of the central engineering problems of space settlement. For now, Earth's atmosphere handles most of this quietly, invisibly. But the Sun has already demonstrated it can overwhelm that system entirely. It has done it before. The evidence is written in fire. On the morning of September 1st, 1859, two astronomers independently watched the Sun and saw something no one had seen before. Richard Carrington, an amateur astronomer in England, was sketching a cluster of dark sunspots through his telescope when a brilliant white light erupted from the surface. He watched it move and fade over about 5 minutes. He checked if sunlight was somehow entering his equipment. It was not. He reported the observation immediately because he had no framework for what he had just seen. Across the Atlantic, another observer recorded the same event at the same time. What Carrington witnessed was the visual signature of the most powerful solar storm in recorded human history. Within hours of that flash, a massive cloud of magnetized plasma, called a coronal mass ejection, was racing toward Earth at over 5 million miles per hour. It arrived in 17 hours, roughly 4 times faster than a typical solar storm. When it hit Earth's magnetosphere, the effects were immediate and global. Auroras lit the skies as far south as Cuba, the Bahamas, and Hawaii. In the Rocky Mountains, the glow was bright enough that gold miners woke up believing it was morning and began making breakfast. In Colombia, people could read newspapers outdoors at midnight by the light in the sky. The auroras persisted for days. These were the beautiful symptoms. The damaging ones were centered on the telegraph network, which in 1859 was the most advanced electrical infrastructure humanity had ever built. Telegraph operators across North America and Europe found their systems overwhelmed by strange, powerful currents being driven through the lines by the distorted magnetic field above. Many telegraph machines began operating on their own, sending garbled messages without any operator input. Some machines continued working even after operators disconnected the batteries, running entirely on the electricity induced by the geomagnetic storm. Other machines caught fire. Fires broke out in telegraph offices as the equipment overloaded. No one died as a direct result of the Carrington event because in 1859, humanity's electrical grid was a collection of wires and simple machines. There were no power transformers, no microchips, no satellites, no GPS-dependent infrastructure, no internet, and no financial systems running on networked computers. That is no longer the case. A NASA-funded study completed in 2008 assessed what a Carrington-scale event would do to modern infrastructure. The report described the potential for widespread collapse of electrical power grids across North America and Europe, with recovery times measured in years rather than weeks. The reason is specific to modern power infrastructure, high-voltage transformers. These devices sit at the backbone of the grid and step electricity up or down for long-distance transmission. They are enormous, custom-built, and not stockpiled. Manufacturing one takes between 1 and 3 years. The United States power grid alone contains several hundred of these transformers. A geomagnetic storm large enough would induce currents that could damage or destroy dozens of them simultaneously across multiple states. Without power, water treatment stops, fuel pumps stop, refrigeration stops, communications collapse, supply chains freeze. The cascading failure from losing electricity for an extended period across a continent has been studied repeatedly by government analysts, and the conclusions in those reports are not comfortable reading. The Sun produced the Carrington event once. Astronomers have since identified evidence in ice cores suggesting that storms even larger than Carrington have hit Earth in the past few thousand years. And the question has never been whether another event like this is possible. The question is only when. And what we still haven't fully prepared for is not just the scale of the storm, but something attached to it that travels faster. Start with a single transformer failing in Ohio. The power goes out across 3 states. Within 4 hours, backup systems at water treatment plants exhaust their fuel. By the following morning, 100 million people have no running water. Within 48 hours, without refrigeration, grocery stores begin discarding their inventory. Within 1 week, fuel shortages ground aviation, halt shipping, and stop most surface transport. Within 1 month, food distribution networks in affected regions have broken down at the regional level. This is the scenario most frequently produced by serious modelling of a Carrington-scale event striking Earth today, and it comes not from sensationalist sources but from the United States National Academy of Sciences, the Federal Emergency Management Agency, and multiple insurance industry risk analyses. The numbers differ by model. The general shape of the outcome does not. The fundamental problem is the high-voltage transformer. Modern power grids transmit electricity across thousands of miles by stepping voltage up to extremely high levels for transmission. then stepping it back down for local use. The devices that do this stepping are large, custom manufactured, and built to precise specifications. Many of the transformers currently operating in the American grid are decades old and were designed to tolerances that did not account for geomagnetically induced currents of the magnitude a large solar storm produces. When a geomagnetic storm hits Earth, it distorts the magnetic field rapidly. That rapidly changing magnetic field induces electrical currents in any long conductor on the ground, exactly as Carrington observed in telegraph lines. Modern power lines are far longer, carry far more current, and are connected to transformers far more complex and vulnerable than Victorian telegraph equipment. The induced currents heat transformer cores, sometimes past their physical limits. The damage can be irreversible. Replacement, as noted, takes years. Beyond the grid, a Carrington-level storm would disable most operational satellites. Spacecraft not designed with sufficient radiation hardening, which includes many commercial satellites launched in the past decade, could suffer permanent damage to their electronics. GPS, which military and civilian navigation now depends on globally, would become unreliable or fail entirely during the storm. The global positioning system is not just for navigation. It provides precise timing signals that financial transaction networks, cell towers, and power grid synchronization systems rely on continuously. Remove GPS timing accuracy, and multiple infrastructure systems experience cascading failures. Airlines would face immediate grounding orders for polar routes where radiation exposure would spike dangerously. Long-distance high-frequency radio communications, a backup system used specifically during satellite and internet failures, would be knocked out by ionospheric disruption simultaneously with the other failures. The backup would fail at the same moment it was needed most. The economic estimate produced in a 2013 Lloyd's of London risk report placed the direct cost of a major geomagnetic storm hitting the United States between $600 billion and $2.6 trillion, with full economic recovery potentially taking 4 to 10 years. This single figure places a Carrington-level event among the most economically damaging natural disasters in recorded history, alongside events that killed millions. The preparation gap is real. While space weather forecasting has improved substantially in recent decades, and government programs now track solar activity continuously, the physical infrastructure upgrades needed to harden the grid against geomagnetically induced currents have moved slowly. Some utilities have installed blocking devices, most have not. The sun fires these storms unpredictably. The lead time between detection and impact can be as short as 18 hours. That is the window. 18 hours to prepare a global civilization. But the sun is not the only threat orbiting us. Something else is out there. Thousands of them. And a few are already aimed directly at Earth. On average, an object the size of a car enters Earth's atmosphere every year. It burns up before reaching the ground. Most people never notice. But scale that object up, add mass and velocity, and the math changes entirely. The difference between a fireball that lights up the sky and an impact that levels a city is a matter of diameter measured in yards, not miles. The threshold for a regional catastrophe sits at somewhere around 150 feet across. At 500 feet, you're looking at potential devastation covering hundreds of square miles. At a third of a mile, you enter the territory of civilization-altering events. As of today, astronomers have catalogued roughly 35,000 near-Earth asteroids, objects whose orbits bring them within about 120 million miles of the Sun, and therefore close enough to potentially intersect with Earth's path. Of these, around 2,300 are classified as potentially hazardous, large enough to cause significant damage, and with orbits that bring them within a relatively close range of Earth on a recurring basis. This is the watched population. The concern is the unwatched one. Current estimates from survey programs suggest that humanity has found roughly 95% of near-Earth asteroids larger than a kilometre in diameter. For anything that size or bigger, the impact energy would be measured in billions of nuclear warheads, and the consequences would be global. That category is relatively well monitored. But for objects between 150 feet and a kilometre in diameter, the completeness of the catalogue drops dramatically. Estimates suggest fewer than 40% of this size range has been identified. These mid-sized objects are the dangerous gap. They are too small to end civilization outright, but large enough to destroy a major city, collapse regional infrastructure, generate massive tsunamis if they hit the ocean, and trigger economic disruption felt globally. There are hundreds of thousands of them. Most have never been detected. The reason detection is difficult comes down to physics and resources. Small asteroids are dark, fast, and often approach Earth from the direction of the Sun, where ground-based telescopes cannot look without being blinded. Many are only discovered days or weeks before their closest approach to Earth, providing almost no preparation time. In 2013, a small asteroid exploded over the Russian city of Chelyabinsk. The shockwave shattered windows across several cities, injured roughly 1,500 people, and collapsed part of a factory roof. It arrived completely undetected. No observatory on Earth knew it was coming. It came from the direction of the Sun. Detection programs have improved since Chelyabinsk. NASA's Planetary Defense Coordination Office now coordinates asteroid tracking, and a dedicated survey telescope called the NEO Surveyor was under development to specifically address the gap in sun direction detection and mid-sized asteroid cataloguing. But as of now, large portions of the near-Earth asteroid population remain unknown. What happens once an asteroid is detected? That question now has a partial answer. In 2022, NASA's DART spacecraft deliberately flew into an asteroid called Dimorphos and successfully changed its orbital period by 33 minutes. This was the first confirmed successful planetary defense test in history. The result confirmed that kinetic impactor technology, essentially ramming a spacecraft into an asteroid, can meaningfully alter an object's trajectory given enough lead time. Lead time is the critical variable. The earlier a threatening asteroid is detected, the smaller the correction needed. Waiting until an object is close requires exponentially more force to deflect. Some asteroids, however, do not give warnings. They arrive without the courtesy of being in our catalogues first. On June 30th, 1908, something hit Siberia. There was no crater, no meteorite fragments found for decades, no warning. The object arrived silently through the upper atmosphere, accelerating as it fell, until at roughly 5 miles above the Siberian forest, it reached the limit of what the atmosphere could compress around it and detonated. The explosion released energy equivalent to roughly 15 megatons of TNT, more than 1,000 times the energy of the atomic bomb dropped on Hiroshima. The fireball was seen from hundreds of miles away. The shockwave circled the Earth twice, detectable on barometers in England. Below the explosion, 800 square miles of forest were levelled. Roughly 80 million trees were flattened outward from the centre, like bristles on a brush pressed to a table. At the epicentre, trees still stood, but they had been stripped of every branch, leaving vertical poles pointing at the empty sky. The force came from above, not from the side, so the trees directly beneath survived as burned stakes while everything around them was knocked flat. The Tunguska region was remote. No permanent human settlements sat beneath the explosion. The closest witnesses were traders and nomadic reindeer herders, several of whom reported being thrown from their feet, temporary blindness from the flash, and heat intense enough to feel like a sunburn from dozens of miles away. One man reported being knocked unconscious and waking to find his shirt singed. Had the object arrived 4 hours later, as Earth rotated, the explosion would have detonated above St. Petersburg. A city of 2 million people in 1908, with dense wooden architecture, would have experienced a fireball visible for 300 miles and a shockwave capable of demolishing every structure across the central city. Scientists have debated the nature of the Tunguska object for over a century. Current scientific consensus, supported by analysis of microscopic spherules found in soil from the region and modelling of the explosion's characteristics, favours a small asteroid or comet fragment, roughly 160 to 200 feet in diameter. An object of that size does not survive passage through the atmosphere. It explodes before reaching the ground. This is why there was no crater and no large meteorite. The object simply ceased to exist as an intact body and released its kinetic energy as heat and pressure. This detail matters enormously for planetary defense. The objects most likely to hit populated areas without warning are precisely the ones that airburst rather than crater. They are too small to be easily tracked. They arrive from unpredictable directions, and they detonate above the surface, spreading their destructive force across a wide area rather than concentrating it at a single impact point. For a coastal city, the shockwave from a Tunguska-scale airburst over the ocean could shatter windows, damage structures, and generate a localized pressure wave felt across the metropolitan area without producing any visible impact. Estimates suggest Tunguska-scale events happen somewhere on Earth roughly every 500 to 1,000 years. Given how little of Earth's surface is inhabited at high density, most will hit open ocean or wilderness. Most. The mathematics of randomness does not guarantee that distribution holds indefinitely. And Tunguska was relatively small. In the orbital architecture of the solar system, something much larger is sometimes pushed directly toward us. And the entity responsible is a planet we think of as our protector. Jupiter is the largest planet in our solar system by a significant margin. It contains more than twice the mass of all other planets combined. Its gravity is the dominant force shaping the behavior of everything in the outer solar system, particularly the asteroid belt that sits between Mars and Jupiter, a region containing millions of rocky bodies left over from the solar system's formation. For most of the history of planetary science, Jupiter was seen as Earth's guardian, a gravitational vacuum cleaner sweeping up dangerous debris before it could threaten the inner planets. The reality is considerably more complicated. Jupiter's gravitational influence does intercept some asteroids. Objects that wander too, close to the giant planet, get captured in its gravity, flung into the Sun, or ejected entirely from the solar system. The comet Shoemaker-Levy 9 famously broke into fragments and was pulled into Jupiter in 1994, producing a series of impacts visible from Earth and leaving scars in the atmosphere larger than our planet. If that comet had been aimed at Earth instead of Jupiter, the consequences for life here would have been catastrophic. But Jupiter's gravity is not a simple one-way shield. It is a gravitational environment that creates as well as destroys. The same forces that can deflect asteroids away from the inner solar system can also redirect them toward it. Orbital resonances, specific patterns where an asteroid's orbital period is a simple mathematical fraction of Jupiter's year, gradually alter the orbit of objects caught in those resonances, pulling them out of the asteroid belt and sending them on new trajectories. Many near-Earth asteroids arrived in their current orbits via exactly this mechanism, nudged by Jupiter's gravity over thousands of years until their paths intersected with the inner solar system. Some researchers have argued that Jupiter's net effect on Earth's impact rate is actually negative, meaning that its gravity delivers more threats to the inner solar system than it deflects. This remains an active area of debate among planetary scientists, and the outcome depends significantly on which category of object is being analysed. For short-period comets, Jupiter does appear to be a net delivery mechanism, capturing distant comets into the inner solar system on orbits that bring them close to Earth. For asteroids originating in the main belt, Jupiter's resonance effects are the primary driver of near-Earth asteroid populations. The practical implication is that the solar system's gravitational architecture is in continuous slow motion. Objects do not stay on fixed orbits indefinitely. Gravitational tugs from planets, including Jupiter, accumulate over thousands of years and gradually shift trajectories. An asteroid that poses no threat today could be in a meaningfully different orbit in 10,000 years. This is why planetary defense planning operates on long-time horizons, tracking not just current positions but the probabilistic spread of possible future orbits, as small uncertainties in position and velocity compound over time. Among the most closely watched near-Earth asteroids is one called Apophis, discovered in 2004. Early orbital calculations suggested a small but non-zero probability of impact with Earth in 2029 and again in 2036. Subsequent observations refined the orbit and ruled out both dates. Further analysis extended the no-impact certainty through 2029, when Apophis will pass within 20,000 miles of Earth, close enough to be visible to the naked eye in some regions. That pass will itself slightly alter Apophis's orbit, making longer-term predictions more uncertain. Apophis is being watched. Most objects this size are not, and some threats come from much farther out, from regions of the solar system so distant that by the time we see them, there may be very little time left at all. In 2017, something entered our solar system that should not have been there. Astronomers at the University of Hawaii detected a fast-moving object passing through the inner solar system using the Pan-STARRS telescope. As they calculated its orbit backward, something unusual appeared in the numbers. Its trajectory was hyperbolic. The object was not gravitationally bound to the Sun. It had come from outside our solar system entirely, travelled through interstellar space for an unknown distance and an unknown amount of time, passed within about 15 million miles of the Sun, and was now exiting on a path that would take it back out into the galaxy, never to return. The object was named Oumuamua, from the Hawaiian word for messenger or scout. It was the first confirmed interstellar object ever detected passing through our solar system. Oumuamua was unusual in multiple ways that generated significant scientific debate. It was elongated, with an estimated length-to-width ratio somewhere between 5:1 and 10:1, a shape unlike any solar system asteroid observed before. As it moved away from the Sun, it appeared to accelerate slightly faster than gravity alone could account for. Most interstellar asteroids would be expected to show outgassing from ICES, which creates a small rocket-like push, but no outgassing was detected. The anomalous acceleration remained unexplained by standard mechanisms. Most researchers attributed the acceleration to pressure from the sunlight acting on an unusually thin, flat object, possibly a fragment of cosmic material shredded and flattened by its journey through interstellar space. A small number of researchers, including Harvard astronomer Avi Loeb, proposed that the shape and behaviour were consistent with a manufactured artificial object. That hypothesis has not been accepted by the mainstream scientific community and remains highly speculative. However, it has not been definitively disproven either, because Oumuamua passed through before any spacecraft could intercept it. In 2019, a second confirmed interstellar object was detected, Borisov, a comet-like body with a much more conventional appearance and behaviour. Borisov had a detectable coma, behaved consistently with an icy body experiencing solar heating, and was generally unremarkable compared to local comets. Its significance was simply that it confirmed interstellar objects pass through our solar system with some regularity. 2 detected in 2 years suggests the actual rate of such passages is considerably higher. Most simply go undetected because they arrive and depart before any telescope happens to be looking in the right direction. The question these objects raise for planetary risk is straightforward. If interstellar objects pass through our solar system periodically, and some portion of them are solid, fast-moving and large, then the category of potential impactors is not limited to objects we have catalogued within our own solar system. An object originating in another star system would arrive on a hyperbolic trajectory, meaning it could come from almost any direction, and would be moving faster than any gravitationally bound solar system object. It would also be detected far later than a comparable local object, potentially only months before closest approach. The probability of an interstellar object actually impacting Earth is extremely low. But the detection and response problem it poses is genuinely different from the asteroid problem. An interstellar impactor gives shorter warning, comes from an unmonitored direction, and travels at velocities that reduce deflection options significantly. What Oumuamua and Borisov confirmed is that the solar system is not a closed box. Things come in from outside, and some of the things from outside our solar system are far stranger than any rock. Somewhere in the galaxy right now, a planet is drifting alone. No star to orbit, no light, no heat from above, just a world-sized body moving through the darkness of interstellar space at tens of thousands of miles per hour, completely invisible against the black background of the galaxy. And based on current scientific estimates, there are more of these wandering planets in the Milky Way than there are stars. Rogue planets, also called free-floating planets, or interstellar planets, form through 2 main processes. Some form normally around stars and get ejected during the violent gravitational interactions of early solar system development, when young planetary systems are unstable and objects are being scattered into new orbits. Computer simulations of solar system formation consistently produce ejections, suggesting that for every planet that stays in a stable orbit, at least 1 or 2 get thrown out into interstellar space during the first few 100 million years. Some rogue planets may also form directly from collapsing gas clouds too small to ignite as stars, essentially failed stars that stopped short of nuclear fusion. These objects have been difficult to detect precisely because they produce no starlight and orbit no detectable parent star. Astronomers have identified them through gravitational microlensing events, moments when a rogue planet passes between Earth and a distant background star and briefly bends and magnifies that star's light in a distinctive way. Analysis of microlensing surveys suggests that free-floating, planet-sized objects may outnumber stars in the Milky Way by a factor somewhere between 2 to 1 and possibly much higher for smaller objects. The closest known rogue planets are hundreds of light-years from Earth. None are on a collision course with our solar system in any time frame relevant to human civilization. But the relevant concern is not direct collision with Earth. A rogue planet passing through or near our solar system would not need to physically strike anything to cause damage. The gravitational influence of a large body passing through the outer solar system could disrupt the Oort cloud, a region of frozen objects at the far edge of our solar system. This gravitational disturbance would redirect comets inward, sending them on new trajectories aimed toward the Sun and the planets orbiting it. The effect would be delayed, measured in thousands to tens of thousands of years between the passage and the arrival of the redirected comets at Earth's distance. But the effect would be real, and it would produce a dramatically increased comet flux through the inner solar system for a sustained period. There is evidence in the geological record suggesting the inner solar system has experienced periods of heightened impact rates, possibly linked to external gravitational disturbances. The mechanism connecting those episodes to specific causes is still being investigated. For direct planetary interaction, a rogue planet close pass would need to come within the inner solar system to meaningfully disrupt Earth's orbit. The mathematical probability of this within a billion-year timeframe is very small. However, small is different from zero in a galaxy with potentially more rogue planets than stars. The detection challenge is significant. Ground-based and space-based microlensing surveys have improved dramatically in recent decades, but a rogue planet on an intercept course with the outer solar system might not be detected until it was already within a few light years, depending on its size and composition. There is a region beyond Neptune that holds far more potential threats than rogue planets alone. A shell of frozen objects surrounding our entire solar system, storing comets in deep freeze, waiting for a gravitational nudge to send them inward. At the very edge of the solar system, beyond Neptune, beyond the Kuiper Belt, there is a region that has never been directly observed. It extends from roughly 2,000 astronomical units away from the Sun to perhaps 100,000 astronomical units out, placing its outer edge roughly 1.5 light-years away and more than a quarter of the distance to the nearest star. Inside this vast spherical shell sit an estimated 1 trillion comets, frozen remnants of the early solar system, preserved in cold storage by the near absolute zero temperatures of deep space. This is the Oort cloud, and it is the solar system's ammunition depot. The comets in the Oort cloud are not in stable orbits the way planets are. They orbit the Sun at enormous distances on extremely elongated paths, barely gravitationally bound, moving so slowly at their farthest points that a small nudge can fundamentally change their trajectory. That nudge can come from a passing star, from the gravitational influence of the Milky Way galaxy's disk itself, or from any massive object drifting close enough to disturb the cloud. When a comet gets nudged out of its resting orbit in the Oort cloud, it begins a long fall inward toward the Sun. This journey can take millions of years, but eventually a comet that started its fall from the outer cloud arrives in the inner solar system, heated by the Sun for the first time in its existence, developing a bright coma and tail as ices vaporize and crossing the orbits of the inner planets. These are called long-period comets. Most have orbital periods of hundreds of thousands to millions of years, meaning they have never been observed before by any human civilization, and their existence was unknown until they appeared. The difference between a long-period comet and an asteroid as a planetary threat comes down to detection time. A near-Earth asteroid has been tracked for years or decades before any potential impact date. A long-period comet arriving from the Oort cloud might be detected only months before its closest approach to Earth. By that point, depending on its trajectory, almost no deflection option currently available to humanity would be sufficient. A comet at 1 mile in diameter would release energy roughly equivalent to 50,000 nuclear warheads on impact. Larger comets dwarf even that figure. The comet that is believed to have contributed to the dinosaur extinction 66 million years ago may have been between 6 and 9 miles in diameter. The energy released in that impact fundamentally altered Earth's climate for years, collapsing food chains from the base up. Some astronomers have proposed that Earth experiences periodic increases in comet flux, possibly linked to the solar system's oscillating path through the galactic plane as it orbits the Milky Way center. As the solar system bobs above and below the plane of the galaxy over tens of millions of years, the varying gravitational environment may periodically disturb the Oort cloud more than usual, sending elevated numbers of comets inward. Some have pointed to a rough correlation between these cycles and the timing of mass extinction events in the geological record. This remains an area of active research rather than established consensus. The evidence is suggestive but not definitive. What is definitive is that the Oort cloud represents an enormous reservoir of potential impactors, any of which can be mobilized with minimal warning by gravitational events happening at the outer edge of the solar system. The comets that arrive from this region are effectively unknown until they appear, and their arrival window is measured in months. A long-period comet is, in some ways, the most challenging planetary threat we face. Unlike asteroids that have been catalogued and tracked over years, a long-period comet arriving from the Oort cloud enters the inner solar system with no prior history in any human database. It has spent potentially millions of years in frozen storage in the outer solar system, completely invisible to every telescope ever built. The first sign of its arrival is the faint smudge of light that appears as its icy surface begins to vaporize under solar heating, typically when it crosses somewhere between Jupiter and Mars in its inward journey. From that first detection to its closest approach to Earth can be as little as 6 months. In some trajectory configurations, the warning window is even shorter. The physics of deflecting a comet differs from deflecting an asteroid in important ways. Comets are not uniform solid rocks. They are collections of ice, dust, and loosely bound material, sometimes described as dirty snowballs, sometimes as icy mud balls. Their internal structure is irregular and poorly understood for any specific comet until one is physically visited. When heated by the sun, they vent jets of gas from active regions on their surface, and these jets provide small but unpredictable pushes to the comet's orbit. Predicting the exact future trajectory of an active comet is harder than predicting the trajectory of an inert asteroid. A kinetic impactor, the deflection method proven by the DART mission, requires years of lid time to change an object's course by enough to miss Earth. 6 months of warning against a comet significantly larger than Dimorphos means no currently developed deflection technology would be sufficient. A nuclear standoff detonation, where a nuclear warhead is detonated near but not on the surface of the comet to push it with a burst of radiation, has been proposed as a faster-acting alternative. This option has never been tested. The engineering requirements for rapidly building, launching, and detonating a nuclear device near an incoming comet within a 6-month window are extreme. There is also the fragmentation problem. Breaking a large comet into smaller pieces using a nuclear device does not necessarily make the situation better. Multiple fragments on slightly different trajectories, each carrying a fraction of the original energy, can be harder to deal with than a single intact body, particularly when detection and response time is already at its minimum. Scientists do monitor the sky for long-period comets. Survey telescopes scan for new objects continuously, and detection capability has improved significantly over the past 2 decades. The Vera Rubin Observatory, now operational in Chile, conducts deep sky surveys across large areas of sky on short timescales, and is expected to dramatically increase the rate at which long-period comets are detected in the early stages of their infell. Earlier detection directly increases response options, but detection capability does not solve the fundamental time asymmetry of the problem. A comet that has been falling toward the Sun from the Oort cloud for 1 million years can only be detected once it has already committed to its trajectory and is close enough to be observed. The outer solar system remains essentially dark. Objects there are invisible. The warning we get is the warning we get. Long-period comets are relatively rare events on human timescales, but the universe does not calibrate its events to human timescales. Something else that does not calibrate to human timescales operates in the spaces between stars, stellar remnants with magnetic fields so powerful they distort the very physics of matter in their vicinity. Imagine compressing the entire mass of our Sun into a sphere roughly 12 miles across. Now give that sphere a magnetic field 1 trillion times stronger than Earth's, strong enough that if one existed halfway between Earth and the Moon, the magnetic force at Earth's surface would strip the iron from your blood and rip apart the atoms in your body. strong enough that at a distance of roughly 600 miles, a magnetar would override the electromagnetic forces holding molecules together. A magnetar is not an exotic theoretical object. They exist. Astronomers have identified roughly 30 confirmed magnetars in the Milky Way, with several times more likely undetected. Magnetars are a specific type of neutron star, born from the collapse of massive stars during a supernova. When a star between about 8 and 20 times the mass of our Sun runs out of nuclear fuel, its core collapses catastrophically in less than a second, compressing ordinary matter to densities where protons and electrons merge into neutrons. The resulting neutron star packs the mass of our Sun into a space smaller than most cities. Magnetars form when this collapse happens with particularly rapid rotation and under conditions that amplify the magnetic field to extraordinary levels during the implosion. A tablespoon of magnetar material weighs roughly 1 billion tons. The neutron star surface, called the crust, is made of crystalline neutron-rich nuclei packed so tightly that it is billions of times harder than steel. When internal stresses build up and cause a fracture in this crust, the sudden rearrangement of magnetic field lines releases energy in a burst that can outshine the Sun by a factor of millions for a fraction of a second. These events are called starquakes, and they produce the most luminous phenomena in the galaxy during their brief duration. The magnetic field does not break so much as it snaps into a new configuration, the way a rubber band can store stress for a long time before suddenly releasing it. The released energy propagates outward as X-rays and gamma rays at the speed of light. In December 2004, a magnetar located in a star cluster, roughly 50,000 light-years from Earth, called SGR 1806-20, experienced one of the largest starquakes ever recorded. The burst lasted less than 1/10 of a second. In that fraction of a second, it released more energy than the Sun produces in 250,000 years. The burst travelled across 50,000 light-years of space, crossed our galaxy, and arrived at Earth. The effects were measurable. Earth's ionosphere, the upper layer of the atmosphere that reflects radio waves, was compressed and disturbed by the incoming burst. Satellites in orbit detected the signal. Physicists on the ground measuring the ionosphere recorded an anomalous disturbance that lasted several minutes. The event was detected simultaneously by numerous spacecraft as the most powerful cosmic event to physically affect Earth since the development of modern scientific instrumentation. The magnetar responsible was 50,000 light-years away. For context, the entire Milky Way is roughly 100,000 light-years across. SGR 1806 was on the other side of our galaxy, and it still disturbed our atmosphere from there. The disruption was minor. Earth survived without any meaningful harm. But the physics of that event establishes a clear and testable principle. A magnetar within a few thousand light-years undergoing a starquake would not produce a minor disturbance. The closest known magnetar to Earth sits roughly 9,000 light-years away. Several others are within 20,000 light-years. None are currently showing unusual activity. But magnetars do not provide warnings before their crusts fracture. Something travelling at the speed of light announces itself only when it arrives. On December 27, 2004, every gamma-ray detector in space simultaneously registered an event so powerful that several instruments went off scale. The burst lasted about 0.2 of a second at its peak. In those 0.2 of a second, Earth received more gamma-ray energy from that single event than from any recorded source outside our solar system in history. Scientists who reviewed the data later calculated that if the magnetar responsible had been located 10 light-years from Earth, instead of 50,000, the gamma-ray intensity at Earth's surface would have been sufficient to cause a mass extinction. The magnetar is catalogued as SGR 1806-20, part of a class of objects called soft gamma repeaters, magnetars that have previously shown lower energy flare activity. The 2004 event was not its first flare, but it was orders of magnitude more powerful than anything previously recorded from any source of its type. Before this event, no instrument had detected a gamma-ray burst of this intensity from within our own galaxy. The closest recorded gamma-ray bursts of comparable power originated in other galaxies, billions of light-years away. What this event revealed was that magnetar flares are not limited to the relatively modest energy releases previously observed. The upper range of what a magnetar can produce is substantially higher than prior observations had suggested. The 2004 flare redefined the known energy output of a starquake and changed how astrophysicists model the maximum possible emission from these objects. The atmospheric effect was measurable and specific. Earth's ionosphere is normally maintained in its ionized state by solar ultraviolet radiation during daytime, and its night-side chemistry is different from its day-side. The December 27th event arrived and ionized Earth's night-side atmosphere to a degree normally only seen during strong solar flares. Something external to the Sun had never been known to produce before. The ionospheric disturbance affected the phase of very low-frequency radio signals used by naval submarines for communication, signals specifically chosen because of their ability to penetrate to depth. Those signals changed, engineers noticed. Multiple spacecraft recorded the event from different angles and distances, and the combined data allowed researchers to reconstruct the geometry and energy of the burst with high precision. It confirmed that the energy was released in a cone-shaped outflow, concentrated in a specific direction rather than radiating uniformly in all directions. Earth happened to be within the cone. That detail is relevant. A magnetar that fires a directed burst is more dangerous along specific axes relative to its orientation than in others. Predicting which direction a future starquake will fire is currently impossible because the internal magnetic field configuration of a specific magnetar is not observable before it ruptures. The 2004 event also prompted a re-evaluation of an older mystery. The Ordovician mass extinction occurred roughly 440 million years ago and eliminated somewhere around 85% of marine species on Earth in one of the largest die-offs in the planet's history. The cause remained contested for years. In 2004, a team of researchers published a paper proposing that a gamma-ray burst within 6,000 light-years of Earth could have depleted the ozone layer enough to expose ocean surface ecosystems to lethal ultraviolet radiation, triggering the collapse. The 2004 magnetar event, arriving from 50,000 light-years away and still measurably disturbing Earth's atmosphere, added a practical data point to this hypothesis. The case has not been fully confirmed. But the physics connecting gamma-ray burst events to your ozone depletion and surface ultraviolet enhancement is well established. The next chapter is where that physics leads when the source is close enough. Somewhere in the observable universe, a gamma-ray burst goes off roughly once per day. Each one releases more energy in a few seconds than the Sun will produce across its entire 10 billion year lifetime. They are the most energetic explosions the universe is capable of producing, and they travel at the speed of light in concentrated beams across billions of light years with enough energy to reshape the chemistry of an entire planet's atmosphere from the other side of a galaxy. There are two main types. Short gamma-ray bursts last less than 2 seconds and are produced when two neutron stars, or a neutron star and a black hole, spiral into each other and merge. The collision releases an extraordinary amount of energy in a fraction of a second, fired outward in two opposing jets along the rotational axis of the merger. Long gamma-ray bursts last from 2 seconds to several minutes and are produced by a specific type of stellar death called a hypernova, when a massive, rapidly rotating star collapses and its core becomes a black hole so quickly that the infalling material forms an accretion disk and twin jets of energy punch through the collapsing star and out into space at nearly the speed of light. The jets are the critical detail. Gamma-ray bursts are not spherical explosions radiating evenly in all directions. They are beamed, firing their energy in two narrow cones. The angle of these beams is estimated at somewhere between 3 and 10 degrees of arc. This means that from any given point in space, the vast majority of gamma-ray bursts in the universe fire in directions that will never intersect your location. You are statistically protected by geometry. The problem is that the universe is large enough and old enough that the statistics work both ways. Earth is one of billions of planets in the Milky Way alone. Over geological timescales, the probability that a gamma-ray burst beam has already swept across this planet is essentially certain. The probability that it will happen again in the future is also real. Detection of gamma-ray bursts is now routine. Space-based observatories including NASA's Fermi Gamma Ray Space Telescope and the SWIFT telescope detect multiple events per week from their origin points in distant galaxies. When a burst is detected, Automated systems alert ground-based telescopes within seconds, and the afterglow of the explosion can be studied in real time. This has allowed astronomers to measure the distances, energies, and beaming angles of hundreds of gamma-ray bursts in detail. What these observations have confirmed is that the energy released in the most powerful long gamma-ray bursts is difficult to fully comprehend in physical terms. A single event detected in 2008, catalogued as GRB 080319b, was visible to the naked eye from Earth for a brief period despite originating approximately 7.5 billion light-years away, more than halfway across the observable universe. Its peak luminosity exceeded the brightness of the full moon as seen from Earth. The object producing that light was an explosion occurring when the universe was roughly half its current age. From 7.5 billion light-years, the event was visible without equipment. The question of what an event like that would do from within our own galaxy is where the scenario stops being abstract. The answer depends on distance, and the threshold for serious consequences is closer than most people would expect. 6,000 light-years. That is the distance at which most models agree a gamma-ray burst beam aimed directly at Earth would strip the ozone layer fast enough and thoroughly enough to trigger a mass extinction. 6,000 light-years sounds enormous. The Milky Way is 100,000 light-years across, but our galaxy contains roughly 400 billion stars. Within 6,000 light-years of Earth, there are millions of them, and among them are the types of massive, rapidly rotating stars that end their lives as hypernovae. Here is what the physics predicts would happen. The initial gamma-ray pulse arrives at the speed of light with no warning. In approximately 10 seconds, the upper atmosphere absorbs the burst energy. Nitrogen molecules throughout the stratosphere are torn apart and recombined into nitrogen dioxide, a brown gas that absorbs visible sunlight and simultaneously catalyzes the destruction of ozone molecules. Within weeks, ozone concentrations in the stratosphere could fall by 50% globally. Over the following months, ultraviolet radiation from the sun, no longer filtered by an intact ozone layer, reaches the surface at levels lethal to most exposed marine phytoplankton and surface organisms. Phytoplankton produce roughly half of Earth's oxygen and form the base of virtually every marine food chain on the planet. Remove them, and the cascade moves upward through the food web. Marine ecosystems collapse from the bottom. Land ecosystems dependent on oxygen levels maintained by phytoplankton experience atmospheric changes over years and decades. The cooling effect of nitrogen dioxide blocking sunlight combines with the warming effect of reduced plant cover to create a destabilized climate that operates on a different equilibrium for thousands of years. The ozone layer does recover, but recovery takes years to decades, and the damage to species unable to survive the transition is permanent. A burst within 1,000 light-years, aimed directly at Earth, would likely be unsurvivable for complex life on the surface. The radiation dose from the initial pulse at that distance would itself be lethal to most surface organisms before the secondary atmospheric effects even began. A burst within 300 light-years could theoretically sterilize the surface. The chance of a gamma-ray burst occurring within 6,000 light-years and beaming directly at Earth in any given century is extremely low. The directional requirement that the burst must be aimed at us within a narrow cone reduces the probability dramatically compared to the raw rate of stellar explosions in the galactic neighbourhood. However, over millions of years, the accumulated probability is not negligible. Some astrobiologists have proposed that gamma-ray bursts may be one of the key factors limiting where complex life can exist within galaxies. The central regions of galaxies, where star density is highest and stellar death rates are greatest, may be sterilized by gamma-ray bursts frequently enough that complex life cannot establish itself before the next event. This is called the galactic habitable zone hypothesis, and it places Earth in an advantageous position in the relatively quiet outer regions of the Milky Way's disk. Advantageous does not mean safe. The geological record has recorded the results of close encounters before. The evidence points toward one of the most dramatic die-offs in Earth's history, and the culprit may have been exactly this kind of event. 440 million years ago, something ended most of life on Earth. The Ordovician period was a time of remarkable biological diversity. The oceans were full of complex organisms, trilobites, brachiopods, early jawless fish, vast reef-building communities. Life had been diversifying for over 100 million years. Then, over a geologically brief window estimated at roughly 1 to 2 million years, somewhere around 85% of all marine species vanished from the fossil record. The Ordovician mass extinction was the second largest extinction event in Earth's history, surpassed only by the Permian extinction 250 million years ago that eliminated over 90% of species. The cause has been debated for decades. Two broad phases of extinction appear in the fossil record, separated by a period of partial recovery. The first phase correlates with a rapid cooling event, linked to the growth of glaciers as the supercontinent Gondwana drifted over the South Pole. The second phase correlates with warming as the glaciers retreated. But glaciation alone does not fully explain the pattern. The first phase of extinction is consistent with rapid environmental disruption coming before the full onset of glaciation. In 2004, two researchers, Adrian Mellott and Brian Thomas, published a detailed analysis proposing that a gamma ray burst within approximately 6,000 light-years of Earth could account for the first phase of the Ordovician extinction. Their model showed that a 10-second burst aimed at Earth would have depleted the ozone layer over the hemisphere facing the source, exposing surface life and shallow ocean ecosystems to sharply elevated ultraviolet radiation. The hemisphere facing away would have been partially shielded during the initial pulse, but would have experienced ozone depletion globally within weeks as atmospheric chemistry redistributed. The prediction their model produced matched several features of the Ordovician extinction record. Graptolites, a group of marine organisms that lived near the ocean surface and were therefore most exposed to ultraviolet radiation, showed disproportionately high extinction rates in the first phase, consistent with a sudden ultraviolet-driven kill mechanism. Deeper water species, more shielded from surface radiation, showed relatively better survival, again consistent with the gamma-ray burst model. The model also predicted that the ozone depletion and its cascading effects on primary productivity would have cooled the planet by disrupting the biological pump that cycles carbon dioxide through the ocean, potentially contributing to the glaciation that produced the second extinction phase. A gamma-ray burst in this interpretation was not just the initial trigger, but the first domino in a sequence that reshaped Earth's climate for millions of years. The hypothesis remains contested. No direct physical evidence of a gamma-ray burst has been found in Ordovician geological layers, though such evidence would be extremely difficult to detect after 440 million years. Other researchers continue to favour purely internal Earth mechanisms, particularly volcanic activity altering atmospheric chemistry, and sea level changes tied to tectonic plate movement. What the hypothesis demonstrates is that the effects of extreme cosmic events do not require physical impact to cause biological catastrophe. A beam of radiation travelling at the speed of light, with no mass, no physical object arriving, no impact crater, can alter the chemistry of a planet's atmosphere in seconds and set off a chain of consequences that plays out over millions of years in the fossil record. The universe fires weapons with no warning and leaves no obvious evidence, and it does not need to aim from very far away to do serious damage. Space weather closer to home has already demonstrated its ability to reach into the systems we depend on every single day. Space weather is not a future problem. It is happening right now, continuously, and the effects are already measured in billions of dollars per year. Every 11 years, the Sun completes a cycle of activity, moving from a period of relative quiet toward a peak called solar maximum. When sunspot counts rise, solar flares become more frequent, and coronal mass ejections launch from the Sun's surface at higher rates and higher energies. The current solar cycle, Solar Cycle 25, reached its predicted maximum ahead of schedule and at higher intensity than most forecasts suggested. The cycle is producing more frequent and more powerful events than the previous cycle, which itself was relatively quiet. In May 2024, Earth experienced the strongest geomagnetic storm since 2003. A series of coronal mass ejections struck the magnetosphere in quick succession over several days, producing aurora visible as far south as Florida and Texas in the United States and across large portions of Europe. The storm was visually spectacular. Underneath the spectacle, infrastructure took measurable damage. Power grid operators across North America and Europe activated emergency response protocols. Satellite operators reported anomalous behavior across dozens of spacecraft. Several precision agriculture systems using GPS guidance experienced positioning errors significant enough to halt operations. Radio communications at certain frequencies were disrupted for extended periods. No grid transformers failed catastrophically during the May 2024 storm. The event was roughly categorized as a severe geomagnetic storm, the second highest category on the current scale. The highest category, an extreme storm, represents an event between 5 and 10 times more powerful. The Carrington event of 1859 was an extreme storm. The 2003 Halloween storms briefly reached extreme levels. These events demonstrate that the current solar cycle is capable of producing conditions far beyond what May 2024 delivered. The aviation industry now factors space weather into operational planning. During major solar particle events, flights operating on polar routes receive elevated radiation doses because the polar regions offer less magnetic shielding. Airlines regularly divert polar routes during solar particle events, adding flight time and fuel cost. A study published by the aviation industry estimated the annual cost of space weather-related polar route diversions in the tens of millions of dollars globally, a routine operational expense treated similarly to avoiding severe weather systems. Satellite operators represent a significant economic stake in space weather. Thousands of commercial satellites currently orbit Earth, providing communications, navigation, remote sensing, and internet services. At altitudes above the inner Van Allen belt, these satellites are exposed to the full particle radiation environment. During geomagnetic storms, satellites experience increased atmospheric drag in low orbits as the upper atmosphere expands, accelerating orbital decay. Electronics experience elevated single-event upset rates. Solar panels degrade faster than baseline under sustained particle bombardment. Insurance claims related to satellite anomalies during storm periods have been documented by multiple insurers. SpaceX reported losing roughly 40 Starlink satellites in February 2022 when a geomagnetic storm elevated atmospheric density enough to increase drag on freshly launched satellites before they could raise their orbits to operational altitude. The satellites re-entered and burned up. This single event demonstrated that a stronger storm could produce losses at a scale that meaningfully disrupts global communications infrastructure. Space weather is the space environment reaching into daily life without most people noticing. The grid still runs, the planes still fly, but the system is being stressed continuously and the stresses are increasing. Something even more fundamental than solar activity shapes the space environment we travel through. Our solar system itself is moving through an unusual region of the galaxy, and that context changes the baseline threat level in ways only recently understood. Our solar system does not sit in typical galactic space. For roughly 5 to 10 million years, Earth and everything around it has been travelling through a region called the local bubble, a cavity in the interstellar medium roughly 1,000 light-years across, where the density of gas and dust is far lower than in most of the galaxy. This bubble was carved out by a series of supernova explosions that went off in this region of the Milky Way over the past several million years, blasting away the normal interstellar gas that fills galactic space and leaving a relatively empty void. The local bubble was identified and mapped in detail by the Gaia Space Telescope, which has been charting the positions and motions of over 1 billion stars with extraordinary precision. Research published in 2022 showed that nearly all of the nearby star-forming regions, places in the galaxy currently producing new stars, sit on the surface of the local bubble rather than in its interior. The expanding shell of gas and dust created by those ancient supernovae appears to have been compressed at the bubble's edge, triggering new rounds of star formation as the shell propagated outward over millions of years. Our solar system sits near the interior of this bubble, shielded from the higher density interstellar environment outside by the bubble's walls. This positioning has consequences for the cosmic ray environment Earth experiences. Interstellar gas acts as a source and modulator of cosmic ray propagation. The low-density interior of the local bubble means that the cosmic ray environment we inhabit is slightly different from what would exist in denser galactic regions. More directly relevant, the supernovae that created the local bubble happened close enough to Earth, and recently enough in geological terms that their effects may appear in the geological and biological record. A team of researchers studying deep-sea sediment cores found elevated concentrations of a specific radioactive ion isotope, Iron 60, at depths corresponding to roughly 2.6 million years ago, and again around 800,000 years ago. Iron 60 is produced in stellar explosions and does not form naturally on Earth. Its presence in marine sediments represents literal fallout from nearby supernova explosions. The 2.6 million year layer corresponds roughly to the onset of the current Ice Age and a major extinction event affecting large marine animals. The connection between nearby supernova radiation and terrestrial biological change is an active area of research. The local bubble also means our solar system is approaching its boundary. As the Sun continues its orbit of the Milky Way, it will eventually exit the bubble's relatively sheltered interior and enter regions of higher interstellar density. That transition will change the interaction between the solar wind and the interstellar medium, potentially altering the structure of the heliosphere, the bubble of solar influence that currently surrounds the solar system and provides an outer layer of protection against interstellar cosmic rays. When the solar system enters a denser region of interstellar gas, the heliosphere may compress, reducing its shielding effectiveness. The timing and specific consequences of this transition are not precisely known, because the structure of the local bubble's boundary is complex and our motion through it is gradual. But it represents a meaningful change in the galactic environment Earth will experience over the next few million years. The universe beneath all of this visible structure carries a component that outweighs everything we can see, and it passes through the planet every second without interacting with almost anything. Everything you have ever seen, touched, or measured represents roughly 5% of the matter in the universe. The remaining 95% is invisible. It does not emit light, absorb light, or interact with electromagnetic radiation in any detectable way. Astronomers can only observe it through its gravitational effects, the way a massive invisible object would bend the path of visible objects around it. This invisible component of the universe is divided into two broad categories: dark matter, which has mass and clusters gravitationally around galaxies, and dark energy, which drives the accelerating expansion of space itself. Dark matter accounts for roughly 27% of the universe's total energy content. Its nature is one of the biggest unsolved problems in all of physics. The evidence for dark matter is substantial and comes from multiple independent sources. Galaxies rotate too fast for their visible mass to hold them together. Without additional invisible mass distributed throughout the galaxy, the outer stars should fly off into intergalactic space rather than orbit at the speeds observed. Galaxy clusters bend light from objects behind them far more strongly than their visible mass predicts. The large-scale structure of the universe, the distribution of galaxy clusters and cosmic filaments, matches computer simulations that include dark matter far better than those without it. What dark matter actually consists of remains unknown. The leading candidates from theoretical physics are weakly interacting massive particles, hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force, meaning they pass through ordinary matter almost entirely unimpeded. If this description is correct, then trillions of dark matter particles pass through your body every second, through the entire Earth, without interacting with a single atom. They are there, they have mass, they exert gravity collectively, but individually they are functionally invisible and harmless under current understanding. Some physicists have proposed more exotic scenarios where dark matter interacts weakly with ordinary matter in additional ways, or where dense concentrations of dark matter could interact with planetary interiors through accumulation over billions of years, potentially contributing to internal heating. These proposals are highly speculative and not supported by strong observational evidence. The mainstream scientific consensus is that dark matter particles, whatever they are, pose no direct physical threat to life on Earth, but the gravitational influence of dark matter shapes the environment we move through at a scale that is difficult to understate. The Milky Way galaxy is embedded in a dark matter halo, roughly 10 times the mass of all the visible matter in the galaxy. This halo extends far beyond the visible disk of stars and gas. As the solar system orbits the galactic center, it moves through varying densities of this dark matter halo. Periodically, the solar system passes through a denser concentration called a dark matter disk, hypothesized to exist in the galactic plane due to the gravitational settling of dark matter over billions of years. Some researchers have proposed that these density variations in the dark matter environment, as the solar system passes through them over tens of millions of years, could gravitationally nudge comets in the Oort cloud. Contributing to the periodic increases in comet flux, some researchers believe they can detect in the mass extinction record. This idea connects the most invisible component of the universe to the most visible consequences in Earth's geological history. Whether that connection is real remains unconfirmed, but the Milky Way contains something even more concrete and immediately dangerous that drifts through it silently, and these ones are not hypothetical. A stellar mass black hole is roughly 3 to 20 times the mass of our Sun compressed into a region smaller than a city. It produces no light. It has no surface that reflects anything. It does not announce its presence. At a distance of more than a few light hours, a stellar mass black hole is gravitationally indistinguishable from a star of the same mass because gravity does not care what form the mass takes. You could replace the Sun with a black hole of equal mass, and Earth would continue orbiting in exactly the same path, in total darkness, without any change in the gravitational environment. There are an estimated 10 million to 1 billion stellar mass black holes in the Milky Way. Astronomers have confirmed several dozen through indirect observations. Black holes in binary star systems where material stripped from a companion star falls inward and emits X-rays as it heats up in the accretion disk before crossing the event horizon. These detectable black holes are only visible because of the companion star. A solitary black hole drifting through the galaxy with no nearby companion is effectively undetectable with current technology unless it happens to pass in front of a background star, creating a gravitational microlensing event. These solitary black holes are called rogue black holes, and they move. When a massive star explodes as a supernova, the asymmetric nature of the explosion often gives the resulting neutron star or black hole a kick, propelling it at hundreds of miles per second in a random direction. Over millions of years, a rogue black hole can cross significant portions of the galaxy, passing through stellar systems, drifting through interstellar space, completely invisible and completely unannounced. If a rogue black hole were to pass through or near the outer solar system, the gravitational consequences would depend entirely on how close it came. At distances beyond several light-years, a stellar mass black hole's gravity would be negligible compared to the Sun's influence on solar system objects. At distances of a fraction of a light-year, orbital perturbations to Oort cloud objects would produce a sustained comet shower lasting thousands to tens of thousands of years. At distances of a few hundred astronomical units, the outer solar system's structure would be meaningfully disrupted. At distances closer than Neptune's orbit, the gravitational interaction would be catastrophic for planetary orbits. The probability of a rogue black hole passing within even a few light-years in the next billion years is very low, given the density of matter in our region of the galaxy. The distances between stars are enormous, and black holes, despite their reputation, do not gravitationally reach out and pull objects in from far distances. The event horizon, the point of no return, is only a few miles across for a stellar mass black hole. Getting close enough for a gravitational encounter to matter requires a genuine geometric near miss in the enormous emptiness of interstellar space. But the population of undetected rogue black holes is large, their positions are completely unknown, and their velocities carry them across the galaxy on paths no current technology can track. The detection challenge is absolute. There is no survey that could identify a dark, cold, solitary black hole moving through the interstellar void unless it happens to align with a background star. This is a known unknown of significant proportions. The galaxy contains potentially 1 billion black holes drifting silently, and we are aware of almost none of them. They are not alone in their invisibility. The universe carries an even stranger type of disturbance, one that does not require any object to move through space at all. On September 14th, 2015, two detectors separated by nearly 2,000 miles both registered a signal lasting a fraction of a second. The signal was a chirp, rising in frequency over 0.2 of a second as the measured distortion of space increased in amplitude and then stopped. Scientists at the LIGO Observatory had just detected a ripple in the fabric of space-time produced by two black holes, each roughly 30 times the mass of our Sun, that had spiraled together and merged more than 1 billion light-years away. The merger happened over 1 billion years ago. The gravitational wave it produced travelled at the speed of light across the universe for over 1 billion years and arrived at Earth, stretching and squeezing the space between the LIGO mirrors by a distance 1/10,000th the diameter of a proton. Gravitational waves are distortions of spacetime itself, produced whenever massive objects accelerate. Binary star systems, pairs of the neutron stars, black hole mergers, supernovae, and even the Big Bang are all sources. Einstein predicted their existence in 1916 as a consequence of general relativity. For 100 years, nobody could detect them because the distortions they produce are extraordinarily small. LIGO succeeded because of engineering precision that required mirrors held stable to within 1/10,000th the diameter of a proton across a 4-kilometre baseline. The gravitational waves detected from black hole and neutron star mergers pass through Earth harmlessly. The distortion they produce is real but minuscule, far below any threshold that would affect matter in any meaningful way. A gravitational wave from a merger at stellar distances rather than galactic distances would be far more powerful, but even then, current understanding suggests the direct physical effect on Earth would be limited. The wave compresses and stretches space in perpendicular directions as it passes, but the effect on physical structures is transient and symmetric, likely leaving no lasting damage at the energies produced by stellar events within the galaxy. What gravitational wave astronomy has opened up is a completely new observational window on the universe. Before LIGO, every piece of information about the cosmos arrived as electromagnetic radiation, visible light, radio waves, X-rays, gamma rays. All of these travel at the speed of light and interact with matter in the intervening space, meaning some sources are obscured by gas, dust, or distance. Gravitational waves pass through everything without interacting with ordinary matter at all. A gravitational wave produced inside a supernova core, the most energetically explosive region in astrophysics, exits through the surrounding star unchanged and arrives at Earth carrying information about the event that electromagnetic observations cannot provide. This matters for understanding threats, because gravitational wave detectors can register events that have no electromagnetic signature, including the mergers of objects that produce no visible light. A neutron star merger detected through gravitational waves alerted astronomers to look in a specific region of sky where optical telescopes then discovered the electromagnetic counterpart within hours, the first multi-messenger observation in astronomy. The universe communicates through channels we're only just beginning to read. Each new channel reveals events we could not previously see, and some of the events gravitational wave astronomy reveals involve the fabric of space behaving in ways that do not appear in any classical physics textbook. The strangest threat of all does not come from a specific object or explosion. It comes from a possibility written into the structure of space itself. The ground beneath your feet feels solid. The laws of physics feel permanent. They may not be. Quantum field theory, the framework underlying all of particle physics, describes the universe as built from fields filling all of space. Every particle is an excitation of one of these fields. The vacuum of space, despite appearing empty, has a specific energy state. In quantum mechanics, a system can exist in a local energy minimum, meaning it is stable against small disturbances, but could, in principle, tunnel through an energy barrier to a lower energy state. If the vacuum of our universe is in such a local minimum, rather than in the absolute lowest possible energy state, it would be called a metastable vacuum. The question physicists have seriously entertained since the 1970s is this: is the vacuum of our universe actually in the lowest possible energy state? Or does a lower state exist? And could our universe tunnel into it? Measurements of the Higgs boson, discovered at the Large Hadron Collider in 2012, provided the key numbers needed to calculate the stability of the electroweak vacuum. The results placed the universe in a region that is technically metastable, meaning the vacuum is stable against quantum fluctuations under normal conditions, but could, in principle, transition to a lower energy state through a quantum tunneling event. The probability of this happening spontaneously in any given region of space in any given billion years is extraordinarily small. Over the current age of the universe, the probability remains tiny, though the exact number depends on physical parameters known only to limited precision. If vacuum decay were to occur, it would begin at a single point in space where a quantum fluctuation caused a bubble of true vacuum to nucleate. This bubble would expand at the speed of light in all directions. Inside the bubble, the fundamental constants of physics would be different. The laws governing atomic structure, chemistry, and the forces holding matter together would no longer apply in their current form. Everything the bubble passed through, every atom, every particle, every structure, would be converted to the new vacuum state. The process is instantaneous from the perspective of anything in the bubble's path. The bubble travels at the speed of light, which means it is invisible until it arrives. There is no warning, there is no defense. The bubble from a vacuum decay event happening in a distant galaxy could be expanding toward Earth right now, and the first indication of its existence would be its arrival. This scenario does not require any external threat, any specific cosmic object, or any physical projectile. It emerges from the quantum mechanical structure of space itself. Most physicists consider vacuum decay a theoretical curiosity rather than a practical concern. The rate calculations suggest the probability is negligibly small on cosmological timescales, and the observation that the universe has existed for nearly 14 billion years without a detected vacuum decay event is itself evidence that the rate is extremely low. Some have also argued that certain high-energy cosmic events, including the most powerful gamma-ray bursts and cosmic ray collisions happening continuously throughout the universe, would have already triggered vacuum decay if the vacuum were marginally stable enough to make it likely. So the universe appears robust. But the robustness is calculated, not guaranteed. The stability of the physical laws we depend on is a measured quantity with error bars. There are threats that operate on timescales where the word threat barely applies, because the outcome is so far in the future that no currently living entity will experience it. But they reshape the context of everything that exists. Our galaxy has a neighbour, and it is heading directly toward us. The Andromeda Galaxy is the nearest large spiral galaxy to the Milky Way, sitting roughly 2.5 million light-years away. It is visible to the naked eye on dark nights as a faint smear of light in the constellation Andromeda, the most distant object a human can see without equipment. What you're looking at when you see it is a galaxy containing roughly 1 trillion stars, moving toward the Milky Way at around 70 miles per second. This is confirmed. The collision between the Milky Way and Andromeda is not a possibility or a projection. It is a measured, observed event already in progress. Astronomers using the Hubble Space Telescope measured Andromeda's motion precisely enough in 2012 to confirm that the two galaxies will have their first close encounter in roughly 4 billion years, with a more thorough merger completing over the following few billion years. The word collision is somewhat misleading. Galaxies are mostly empty space. Stars are separated by such vast distances that during a galactic merger, actual physical collisions between individual stars are extremely rare. The Milky Way contains several 100 billion stars distributed across a disk roughly 100,000 light-years across. On average, stars in our neighbourhood are separated by several light-years. During the Andromeda merger, the probability of any specific star, including our Sun, physically colliding with another star is very small. What is not small is the gravitational disruption. As two galaxies of comparable mass interpenetrate, the gravitational interactions are complex, violent, and sustained over hundreds of millions of years. Stars on the outskirts of both galaxies are the most vulnerable to being gravitationally flung into new orbits, some into the intergalactic void entirely. The Sun sits in the outer regions of the Milky Way's disk, not the dense central bulge, making its long-term orbital behaviour during the merger harder to predict. Computer simulations of the Andromeda-Milky Way collision consistently show that the Sun's orbit will be significantly altered by the encounter. In some simulations, the Sun ends up in a stable orbit in the merged galaxy. In others, it is ejected into the outer halo far from the galaxy's centre. In a small fraction of simulation runs, the trajectory is more dramatic. The specific outcome for our solar system depends sensitively on precise gravitational calculations that become unpredictable over billion-year timescales. The Sun and Earth will also, independently of Andromeda, face changes within 4 to 5 billion years as the Sun exhausts its hydrogen fuel and expands into a red giant swallowing the inner planets. Earth's prospects 4 billion years from now involve challenges from both within the solar system and from the broader galactic environment simultaneously. 4 billion years is not a human timescale. But the collision illustrates a point about the universe that applies to shorter timeframes as well. Large-scale structure is not static. Galaxies are moving, space is dynamic, and the forces that move galaxies are also moving something much closer to us, a gravitational anomaly so massive it defies intuitive comprehension. Every galaxy within roughly 250 million light-years of Earth is moving in the same direction, including ours. The Milky Way, Andromeda, the entire local group of galaxies, the Virgo cluster, and dozens of other galaxy clusters are all streaming toward a single region of space at speeds of hundreds of miles per second. This flow was first detected in the 1980s when astronomers noticed that galaxies across an enormous volume of space were not moving randomly, as would be expected from a uniform universe. They were drifting collectively towards something. The source of the gravitational pull was hidden behind the plane of the Milky Way, making direct observation difficult because the galaxy's own gas, dust, and stars block the view in that direction. Astronomers eventually mapped enough of the structure to determine that the pull originates from a gravitational concentration they called the Great Attractor, located roughly 150 million to 250 million light-years away in the direction of the Centaurus and Norma constellations. It represents an enormous concentration of mass, possibly amounting to the gravitational equivalent of several quadrillion solar masses. Subsequent surveys revealed that the Great Attractor itself is part of an even larger structure called the Laniakea supercluster, mapped in detail in 2014, using the motions of thousands of galaxies as a gravitational flow map. Laniakea spans roughly 520 million light-years and contains the mass of 100 million billion suns. The Milky Way sits near its outer edge, gravitationally connected to a structure so large it would take light over 500 million years to cross. The practical consequence for Earth is essentially zero on any timescale relevant to human civilization or even the existence of complex life. The cosmic flows pulling galaxies toward the Great Attractor operate on timescales of billions of years and involve gravitational forces distributed so broadly that local planetary systems are entirely unaffected at human scales. What the Great Attractor reveals is the hierarchy of forces operating on the cosmos. Above the scale of individual stars and supernova, above the scale of galaxy collisions, the universe is structured by large-scale gravitational flows operating on scales the human mind was not built to intuitively grasp. These flows shape where matter concentrates, where star formation occurs, where galaxies cluster, and therefore where the conditions for complex life can arise. The Milky Way is not drifting randomly. It is embedded in a gravitational web extending hundreds of millions of light-years in every direction. And that web has a structure. It is one of the most visually striking structures ever mapped, and it connects every galaxy in the observable universe in a pattern that mirrors something found in biological tissue. Stand far enough back from the universe, and it looks like a brain. The large-scale structure of the cosmos consists of vast filaments, sheets of galaxies, and clusters connected at nodes, interspersed with enormous empty voids where almost nothing exists. This structure, called the cosmic web, emerged from tiny density fluctuations in the early universe, and has been amplifying under gravity for nearly 14 billion years. The densest filaments contain thousands of galaxies strung along threads of dark matter, hundreds of millions of light-years long. The voids between them can be 300 million light-years across. Our position in this web shapes the environment the Milky Way experiences. The galaxy sits in a region of moderate density, connected to nearby clusters by filaments that channel the slow flow of matter across cosmic distances. This position is not exceptional by cosmic standards. There are hundreds of billions of galaxies in the observable universe, and most sit within similar web structures. What makes the web relevant to Earth's circumstances is that the local density environment determines the rate of galaxy interactions, the frequency of gravitational disturbances, and ultimately the rate of energetic events that can affect planetary systems within the affected galaxies. Galaxies at the dense nodes of the cosmic web, where filaments intersect, experience higher rates of galaxy-galaxy interactions, elevated star formation, and higher rates of energetic events like gamma-ray bursts and supernovae. The Milky Way's relatively quiet region of the web contributes to the comparatively low rate of extreme energetic events in our galactic neighbourhood. Comparatively low is not the same as absent. The web also governs dark matter flow, and some theorists have proposed that the movement of the solar system relative to the dark matter density variations in local filaments could contribute to long-term periodic changes in the cosmic ray environment and possibly Oort cloud disturbances on timescales of tens of millions of years. The cosmic web is also expanding. Dark energy, the component of the universe driving the accelerating expansion of space, is gradually stretching the distances between filaments, pulling galaxy clusters apart at the larger scales over billions of years. The voids grow, the filaments thin. The web becomes more diffuse as the universe ages. This expansion does not threaten Earth on any relevant timescale, but it leads directly to the endpoint of the physical universe, a state so different from the current cosmos that the word strange fails to capture it adequately. Before we arrive there, the cumulative picture of everything we have covered demands a direct look at probabilities. Multiple extinction-level threats exist simultaneously, and several of them overlap in ways that compound risk rather than reduce it. Everything we have ever seen or measured fits inside a sphere roughly 93 billion light-years across. Not because the universe ends there, but because light from farther away has not had time to reach us in the nearly 14 billion years since the universe began. The edge of the observable universe is not a wall or a boundary. It is a horizon, set by the age of the cosmos and the speed of light. Beyond it, the universe almost certainly continues, possibly forever, but the information it contains cannot reach us. The region just beyond our observational horizon is of significant theoretical interest, because the physics operating there should be, according to all current cosmological models, identical to the physics operating here. The same fundamental constants, the same quantum fields, the same forces. This is an assumption embedded in our models, not a confirmed observational fact because we cannot observe it by definition. Some cosmological models predict that the universe is not only larger than the observable region, but infinitely large. In an infinite universe with a finite number of possible quantum states within any finite volume, every possible arrangement of matter must repeat somewhere. Given sufficient distance, there exist other regions statistically identical to our observable universe, and within them, statistically identical solar systems, planets, and histories. This is called the Level 1 multiverse in physicist Max Tegmark's classification, and requires no exotic new physics, only an infinite universe, which current inflationary models of the early universe suggest is likely. Inflation, the theory that the universe underwent an extraordinarily rapid expansion in the first fraction of a second after the Big Bang, also predicts that other causally disconnected regions of space-time may have undergone different rates of inflation, producing regions where the fundamental constants of physics took different values. In some of those regions, the physics governing atomic structure, chemistry, and complex matter could be fundamentally different from ours. These ideas operate at the boundary between established cosmology and speculative theory. They are taken seriously by professional physicists because they emerge from equations that describe the observable universe extremely well. They are not confirmed because by their nature they make predictions about regions we cannot observe. What the edge of the observable universe represents, in the context of this story, is the limit of information. Every threat discussed in this series is something about which we can, in principle, gather data. We can model it, measure it, and plan responses. The universe beyond our horizon is information dark. If physics there is identical to here, these same threats exist everywhere throughout a potentially infinite cosmos, operating on the same timescales, producing the same kinds of events. The hunting ground does not end at our observational horizon, and within the observable universe, the most fundamental process of all is already underway, operating continuously at every scale, and it has only one direction and one final destination. Every process that has ever occurred in the universe has increased the total amount of disorder in the cosmos. This is not a tendency, it is a law. The second law of thermodynamics states that in any closed system, entropy, the measure of disorder and unusable energy, always increases or stays the same. It never decreases spontaneously. Every star that burns, every explosion that fires, every chemical reaction that powers a living cell moves the universe incrementally but irreversibly toward a state of maximum entropy, a condition physicists call heat death, where energy is distributed so uniformly across space that no temperature differences remain anywhere and no further work can be done. Heat death is not a dramatic explosion or a collision or a sudden event. It is a process, an extremely slow, extremely patient, entirely unavoidable process written into the deepest structure of physical law. Stars are the primary engines of order in the current universe. They pull matter together through gravity, compress it into fusion reactions, and release enormous amounts of structured energy over billions of years. The Sun will burn for another roughly 5 billion years before exhausting its hydrogen supply. Smaller, cooler stars called red dwarfs, the most common type in the galaxy, will burn for trillions of years. Some of the smallest red dwarfs will still be burning long after the last large star has gone dark, perhaps for as long as 10 trillion years from now. After the last stars die, the universe enters a period dominated by stellar remnants. White dwarfs, slowly cooling toward the temperature of their surroundings, neutron stars radiating away their residual heat over unimaginable timescales, and black holes. Black holes are the last structures of concentrated mass. Even they are not permanent. Stephen Hawking demonstrated theoretically in the 1970s that black holes slowly radiate energy as quantum mechanical fluctuations near the event horizon create particle pairs, one of which escapes and carries away energy. This process, called Hawking radiation, is extraordinarily slow for large black holes. A stellar mass black hole would take longer to evaporate than the current age of the universe, raised to the power of 60. A supermassive black hole at the centre of a galaxy would take incomprehensibly longer. But it ends. Everything ends. After the last black hole evaporates, the universe will contain only a diffuse gas of photons and fundamental particles scattered across an unimaginably vast and cold space. No temperature gradients, no chemical reactions, no structures of any kind, entropy at maximum. The laws of physics will still apply perfectly, but nothing will happen, because nothing can happen. The universe will have reached a state of complete thermodynamic equilibrium, and will remain there, unchanged, for the rest of time. This endpoint is as certain as any prediction in all of science. The only variable is the timeline measured in numbers with so many zeros after them that writing them out is meaningless. Against that backdrop, every threat discussed in this series is a local, short-term disruption on the way to the same destination. The heat death is the context, everything else is what happens before it. And in the space between now and that final stillness, all of the threats we have catalogued overlap and interact, pointing at a single unavoidable conclusion about the civilization that currently exists on Earth. Threats do not wait their turn. Every force described in this series is operating right now simultaneously. The Sun is continuously outputting solar wind. Cosmic rays are passing through your body at this moment. Tens of thousands of near-Earth asteroids orbit in catalogued paths, and hundreds of thousands more have never been detected. Long-period comets are falling from the Oort cloud continuously, discovered only when they cross into the inner solar system. The geomagnetic field is measurably weakening. The magneteer that produced the 2004 flare is still active. Gamma-ray bursts are firing in distant galaxies at a rate of roughly one per day, the vast majority aimed away from us, but not all. Risk analysts describe this kind of situation as a compound threat environment. Multiple independent low-probability, high-consequence events exist simultaneously. The probability that any one of them occurs in a given century may be small. The probability that at least one of them occurs over 1,000 years is considerably larger. Over 10,000 years, the probability that at least one of these forces disrupts complex civilization becomes difficult to calculate but meaningful. Over 1 million years, it approaches certainty for some of the threats discussed. Civilizations do not typically plan over geological timescales. Human institutions, governments, and research programs operate on timescales of years, decades, and occasionally centuries. The planetary defense programs that track near-Earth asteroids are a direct response to a recognized compound risk. The probability that an undetected object will eventually enter a threatening trajectory is acknowledged, the consequences are modeled, and detection and deflection research is funded accordingly. This represents one of the most concrete examples of civilization-scale risk planning currently operating. Space weather prediction serves a similar function. Agencies in the United States, Europe, and Japan now operate continuous solar monitoring and forecasting systems specifically to provide warning time for grid operators, satellite controllers, and aviation planners before major geomagnetic events. The warning time is short, the predictive accuracy is limited, and the infrastructure hardening against worst-case events is incomplete. But the framework exists. For other threats discussed in this series, the preparedness gap is larger. No early warning system exists for long-period comets, arriving with less than 1 year of warning, against which current deflection technology would be insufficient. No plan exists for a magnetoflare from a close source, though no close magnetar is currently active. No preparation exists for vacuum decay, because no preparation is possible. These represent acknowledged gaps between the threat landscape and the civilization's current capacity to respond. The compound nature of the threat environment means that even a civilization that solves every individual threat problem still faces the cumulative probability that something in the full threat distribution will eventually exceed its preparation level. This is not a counsel of despair. It is a structural argument for the necessity of becoming a multiplanetary species. A single-planet civilization, however advanced, has zero redundancy against planet-level events. A civilization distributed across multiple planets, moons, and eventually star systems breaks the single point of failure architecture that makes every threat on this list relevant. The history of life on Earth is a record of near misses and recoveries, of lineages that survived mass extinctions by luck of position, behavior, or biology. Asteroids have hit, solar storms have fired, supernovae have gone off, life continued. But life continuing does not guarantee civilization continuing. The gap between biological survival and civilizational continuity is large. Recognizing that we live inside a threat environment is not pessimism. It is the most accurate description of the situation. The question that follows is not whether these threats exist. The question is what a species that understands them is going to do about it. The most significant planetary defense achievement in human history happened in September 2022. A spacecraft called DART, roughly the size and mass of a vending machine, travelled 10 months across space and collided with an asteroid called Dimorphos at roughly 14,000 miles per hour. Dimorphos is a small moon, orbiting a larger asteroid called Didymos, and neither posed any threat to Earth. The mission was a test. The result confirmed that kinetic impact technology works. The collision shortened Dimorphos' orbital period around Didymos by 33 minutes, exceeding the mission's success threshold of 73 seconds by a factor of more than 20. Humanity had successfully changed the motion of a solar system body for the first time. This was genuinely significant. Before DART, planetary defense was theoretical. After DART, it is demonstrated capability. The European Space Agency followed with its HERA mission, currently en route to study the Dimorphos system in detail and extract engineering data that will inform deflection planning for future threatening objects. The NEO Surveyor Space Telescope, developed specifically to detect near-Earth asteroids approaching from the direction of the Sun, where ground-based surveys are blind, represents the most critical gap in the current detection infrastructure and has been a focus of NASA planetary defense investment. Detection is the foundation on which all deflection depends. An asteroid you know about with 10 years of warning requires a tiny nudge to deflect. The same asteroid with 10 days of warning requires a nuclear warhead and may still hit. Solar storm preparedness has advanced in the years since the 2003 Halloween storms. The NOAA Space Weather Prediction Center now operates 24-hour monitoring and issues forecasts for geomagnetic storms, solar particle events, and radio blackouts. Some power utilities in North America and Europe have installed geomagnetically induced current monitoring systems and blocking devices on critical transformers. The percentage of the grid with such protections remains low. The most vulnerable high-voltage transformers, the ones whose failure would cascade into regional blackouts lasting months, are not stockpiled in adequate numbers and cannot be rapidly manufactured. The gap between what is technically feasible in terms of grid hardening and what has been implemented is primarily a policy and investment gap rather than a technical one. The knowledge of what a Carrington-level event would do to the grid has been public, detailed, and specific for over 15 years. The political and financial will to fully implement the available protections has not matched the risk assessment. Space-based threats at the longer and more exotic end of the risk spectrum, magnetoflares, nearby supernovae, gamma-ray bursts, have no current mitigation pathway. These events are detected after the fact. A nearby gamma-ray burst would arrive at the speed of light with zero warning time. The response to these risks, to the extent a response is possible, is not deflection or infrastructure hardening. It is redundancy, spreading complex life and civilization beyond a single planet so that a catastrophic event affecting one location does not end the project entirely. Human presence beyond Earth currently extends to low Earth orbit, maintained continuously since 2001 with the International Space Station, and will extend to the Moon in the coming years through the Artemis program. Mars is the target for crewed missions in the decade ahead. These are the first steps of a very long journey toward genuine civilizational redundancy. The threats in this series are not equally probable, equally distant, or equally addressable. Some we have already partially solved, some we are working toward, some we cannot address with current physics. All of them exist, all of them are real, and all of them are part of the same fundamental reality. The universe is not a safe environment, and it was never designed to be. We were not placed here and given a guarantee. We arrived here through 4 billion years of life, finding ways to survive in a cosmos that was actively trying to kill it. Every extinction that happened reshaped the survivors. Every mass die-off cleared space for what came next. The lineage that produced human intelligence has been through asteroid, impacts, ice ages, supervolcanoes, and magnetic reversals and came through everyone. That resilience is real. But it was the resilience of biology, not of civilization. What we have now that life never had before is awareness. We can see the threats, we can measure them, we can calculate probabilities, build telescopes, launch spacecraft, and begin the long process of spreading beyond this single fragile world before the next Carrington, the next asteroid, the next gamma-ray burst decides this time is its time. Space is hunting us. It has always been hunting us. The difference now is that we finally know it,